In this lesson, we shall focus on linear algebra, the module MAM2000W 2LA linear algebra. We shall look at past examination questions with a specific focus on the June 2024 exam question paper. Right, so we shall quickly move to the fourth question because that's what we're doing.
Yeah.
Right, yeah, we shall quickly. Oh, okay. This thing just popped like that because it is okay. It's the earlier recording. It's the recording that okay. Right. So this is the first one, and then now we did that. Part B is this one here. Right. So let R3 have its usual inner product. Right. That is the dot product, and D. Right. Right. And DB, they said with two vectors. Right, find a basis for the subspace D-perp, which is the orthogonal complement of D that contains all the vectors V in R3, such that V is perpendicular to U, or V is orthogonal to U for every U in D. Okay, so this is just one notation of the orthogonal vectors, okay, or perpendicular vectors. Right, obviously we use the word orthogonal mostly for higher dimensions, and the word perpendicular is actually used when we dealing with basic dimensions, something that is very key. Right. All right, so we continue. Right, so in the end, then we have the following. Right, we have the following. Right. Now, at this point, what we then have is we then need to find a basis for the subspace D-perp. Right, so to find a basis for the subspace D-perp, we proceed as follows. Now, the couple of things, obviously, that remain very, very important at this point. So what do we then do here? Right, so what we then do is we consider vectors. Right, so we consider vectors and then say we have the following vectors. Right. Now, to find a basis for D-perp, because D we already know, but we don't know D-perp. Right, so, and to counter for this, what we then do is the following. Right, we then say, we let consider some vector, and we can give them a name, A, B, C. And this vector be an element of what? Of D-perp, like this. Right, so in the end, then what we then have here becomes the following here. Right, so we then say that, let that be the case, then we are able to do the following. Okay, right, we're able to do the following. Then, because of this, we use the dot product. So you're going to find the dot product of this with that. So you then say that the dot product of the ABC dot, right, if you say dot product of ABC dot, right, so you have ABC dot, this first vector here. Right, so you have exactly that. So now, okay, yeah, okay, I'm just communicating to you now, but there's another student who is pestering me in ways you can't believe. Okay, so now we find the dot product here. You know, this guy sometimes, this student, if he sends me messages, he wants me to reply now. Okay, and now I'm trying to reply to him. Yeah, okay, so you have the dot product of this vector with that. But simultaneously, then we also have the ABC, and then we take the dot product with 0, 1, 1, and therefore this is what? Is 0. So you have the dot product like this. But now if you're taking the dot product like this, why is the dot product 0? It is 0 because of this side. They are perpendicular vectors. Okay, good. And then with that, then the dot product is component wise. So which means that that is the case. Thus, the dot product is component wise. So it's like A by 1, B by 1, C by 0, 0. And for the first one. And now for the second one, it's going to be A by 0, B by 1, and C by 1 equals 0, like so. And this means that we have A plus B is 0, and you have B plus C is 0. You get the point? And then with this, then we have a set of equations that you can use. And now this means that with A is equal to what? A is equal to minus B, and B is equal to minus C. Right, like this. And with this, then, if you have this, what then can we be able to achieve out of this? Well, in general, what you need to take into account is that this is an example of a basis situation. So now you'd have the 1, 1, 0. Okay, for this one, 1, 1, C, there's no C here. And then here in the second case, you'd have 0, 1, 1. Okay, in general, you need to row reduce these things. When you have a set of equations like this, you need to find the basis. You need to simplify these. Okay, otherwise then you have redundant variables there. And then now, obviously, it's a little bit strange, this one, but it's okay, because there are 2 equations in 3 unknowns, not balanced. Okay, but it's okay. We have no choice. This is the question we've been given. But now, normally, if you have 3 equations, if you have 3 unknowns, you must have 3 equations. Okay, right. So let's continue. Now we have this one. So we need to get what here? We need to get a 0 there. Row 1 minus row 2. 1, 0, 0, 0. 0, 1, 0, 0. Okay, so now this one is perfect. It's actually in reduced zero echelon form. With that, then we're able to continue and achieve the following, right? Which means that you have A is 0 and B is 0. Okay, because like A, B, and then what about C? C, you can call it C. You can call it C. Okay, normally my lecturer used to just say, you know, okay, for the free variable, for the free variable. Okay, right. So now, then with that, but now you can call it T, where T is the real number. Right now you have the vector A, B, C, and then now the A is 0, and then you have what exactly?
B 0.
B 0, and then the C is what?
1.
This
It's T.
1. Yeah, it's T. Well done. It's T, like this. Okay. Okay, now we're going to test these things. We're going to test these things here. And then with this, then you have T outside, which is 0, 0, 1, like this. Okay. So which means, therefore, what does it mean? It means that the basis, right, so I'm going to just divide here. The basis for, this is very interesting. For D perpendicular, I'm going to discuss this in detail now. Okay, the couple of dimensions of this that we're going to look at. In case the student does not simplify the equations, what happens? In case the student does not simplify the equations, what actually happens here? Okay, so yeah, it's something that we're going to discuss right now together. All right, so you're going to have that. So, but now this is going to be exactly 0, 0, 1. Okay, but we need to test these. Is this what works or not? In other words, if you check, does this work? Does this not work? And what exactly do we have? Okay, there's a small mistake. There's a small mistake. Okay, check out. Okay, there's a small mistake I'm seeing because here we have 110, but here for the second one must have 011.
Oh,
Okay, I'm wondering why I put a 0 there because I'm seeing that it's a bit strange. Okay, but now if you see this one is 110, and then this one must be 0 for A because there's no A, and then you must have 110. Okay, so it's gonna affect. So yeah, I'm gonna make some changes here. Okay, it's gonna actually make some changes. So let us make a couple of changes here. So okay, I'm because I can see that doesn't make sense. Okay, I had to
why?
test this. Please
But
come again.
because it's supposed. Well,
Yeah.
how can you see that it doesn't make sense?
Well, it would make sense if you take the dot of this one with the basis, then the result must be 0. You know, but I could see that the result was not 0, so I was wondering that
Okay.
something is missing. Okay, right. So now, and that is why they. But now here, because you have this one is 110, and then this one it's 011. Okay, so let's remove this one. So now let's come to this one. Okay, if you come to this one, now you need to get a 0 here, which means you have row 1 minus row 2. 1, and then minus row 2, you get a 0 here, you have minus 1. 0. Okay, and then you have 0, 1, 1, 0. Okay, now, okay, because now, is this one in reduced row echelon form? Is there any form of reduction that is possible? There's no reduction that is possible here.
No.
Okay, right. Because of that, then we're able to therefore make the following conclusion and then say A is equal to what? So A is equal to C for this one, because you can see it as A minus C is 0. So A is equal to C. And then for this one means B and C. So you can see it as B equals minus C, like this. Good. And with this, then we're able to make, so, okay, what about C? Because C is so you can say C is equal to C. Okay, right. And then if you make C equal to T, then this one is going to be minus T, and this one is going to be T. Okay, where this T is a real number. Okay, now it means that you can have the A, B, C. All right, so what is the A? The A is T. The B is minus T. The C is T. Okay, so this one is going to work. But now, once again, if you do this, you can do this in many ways. So, but this one is going to work. There are two possible bases. Okay, you can first pull out T, which is the natural way of doing it. Okay, if you first pull out T, which is the natural way of doing it, right, so what do we then get if you first pull out T? So if you first pull out T, then you're going to have 1 minus 1, 1, correct. But then you can also pull minus T out. If you pull minus T out, then you have minus 1, 1, minus 1, like this. Okay, so there are some bases that, I mean, there are more than these, but in other words, you can then say a basis, right? So a basis for DPEP is what? So you can write the basis is the first one, which is 1 minus 1, 1, like this, or minus 1, 1, minus 1. You can write it like this. You get the point. So in any event, then if you dot this one, with any of these, it must be 0. You can do a check.
Okay.
Yeah, you can do a quick check. Right. So in other words, you have that D is like this. It's containing 1, 1, 0. And then it's also containing 0, 1, 1. Okay. Now you have got that DPEP D pep is going to contain what? It's going to contain this one. Right, it's going to contain 1 minus 1, 1. Right, 1 minus 1, 1. Or D pep consists of the negatives, right? Which is minus 1, 1, minus 1. Minus 1, 1, minus 1, like this. You get the point? So, so now we continue. We need to check. We can check these things. Now, to do a quick check, which examiner does not quite expect, let's dot this one with this. We are first taking this D pep because the D we know is already given. So the D is correct. But we need to check our own that we got. Right. So the 110, if you dot it with this one, 1 minus 1, 1. What is the answer here? So this one you got, okay, yeah, because 1 times 1 is 1. This one and this one is minus 1. And the 0 by 1 is what? Is a 0. And and this is a 0. Meaning that indeed, but it must also produce 0 with this one. So which is 0, 1, 1. And then we have 1 minus 1, 1. 0 by 1, 0. 1 minus 1 plus 1. And the result is 0. So, and this confirms that this D pep is correct. You know, the orthogonal complement, this one is, this basis is correct. But also, you can also check this one is surely correct. How? Okay, if you dot this one, and obviously you dot them in a, right, so yeah, in commutative manner, right, you dot this one. 1 and minus 1 is minus 1 plus 1 minus 0, which is 0. And then now you also dot this one here. This you have 110, then you have 0, 1, 1. You dot with minus 1, 1, minus 1. If you dot this one and this one, you have a 0. This one and this one, you have a 1. This one and this one, you have a minus 1. Right, so, okay, let us check this one. Okay, we're just checking. Okay, so yes, say this one is 0, and then this one is 1, and then this one is a minus 1, and then for the result is 0. So you're able to see that indeed these bases, these are both correct. So a student can write any of these, but I can see that your lecturer wrote this one. Okay, yeah, because of the way they did it, but yeah, it's the same thing anyhow. All right, so we continue right now, please, to do the next thing. Let us check the next question. Right, we check the next question. The next question is part C. Okay, this is the one I was talking about. Okay, where they just have put some things here, like the V plus U and the U plus W. And then now, obviously, they need the length, but the length is not the usual one. Okay, but now the examiner is saying, let V be an inner product space, and you have the U, V, W, B vectors in V, which are elements of V, the inner product space. You are given that the inner product is minus 1, it's 2, it's minus 2, it's the length is 5, the length of U is 5, the length of V is 3, the length of W is what? Is 4. Now find V plus U, and also the inner product of V plus U and U plus W. Okay, some 2 marks. Sometimes there are 2 million. Okay, right. Yeah, yeah. Sometimes there are 2 million comes to the marks. Okay, but you see, this is a gross injustice because it means that to finish this exam, you don't need to write too much. You need to write like key things. Otherwise, if you write lots of details, you just can't finish. Okay, just can't finish. Okay, so now let us look at this one. There are two problems we need to solve here. Okay, in this question, we need to what? Find this and that one. Okay, let us find first this one. Like I said earlier, to find this one, which I saw here, what do? You
separate.
Yes, you separate, you expand. But you can look at this one as one vector and then expand. So if you treat this one as one vector, you don't separate them. So you then gonna have V, and then this one you keep as one vector. Plus, and then you have U, you keep this one still as one vector, like this. And then now you expand this, In the way you expand this, you say VU VW. Okay, now this is one vector, just expand into that. So it's UU, and then it's UW, like this.
Yeah.
Okay, so
And
what
then
is VU? Okay, because now you already have
-1.
it's -1. Well done. Right, and then what is VW?
It's 2.
Well done. It's 2 exactly. Then what
And
is
then
UU?
5 squared.
Okay, well done, well done. Because now here, obviously, is that the length of U is the square root of UU.
The
Like,
inner product of UU.
yes, the inner product of UU. And then this length is 5. So that now, at this point, if you have only UU alone, then you square both sides. I mean, I'm just justifying the fact that you square both sides, getting that. So that the UU, therefore, is going to actually become like 5 squared. What about UW? It's -2.
-2. Yeah.
Right. So you can put a -2 there.
So
Yes,
can
please.
I ask,
Yes, please.
the
Now,
inner product of U and UV and the inner product of VW, is it the same?
which one, please? Which one?
If you swap the order around,
If you
is
swap
it
the
the
order
same thing?
around. Okay,
Yeah.
that's a good question. In general, it's not the same thing.
Okay.
Right. So, okay, I'm gonna discuss that. There's something I want to mention in connection with that. I'm gonna mention that. Let's just simplify this one here. Okay,
Okay,
-1
no
plus
problem.
2 is what? It's 1 plus. Okay, you can simplify this. This is 1, and then this is 25 minus 2. 25 minus 2 is what? It's exactly
It's
23 plus
23.
1 is 24. Okay.
24.
So now it looks like obviously we're getting 24, and the 24 is actually the correct answer. Okay, I'm going to discuss the properties of the inner product very shortly in line with the question. Okay, right. If you look at the next thing, so this one we have got the answer. The answer is a 24, which is indeed correct. Then the next thing is to deal with this one, the length of this. Right. So to find the length of this, let us find exactly the length of that. So to find the length of this, this paper was quite a very hectic paper, I think. Okay, because it was a bit different from the former ones. Because before they could just say find the length of V alone. You get the point. Okay, but I'm looking at the fact that right now they are looking at like something a little bit more. So now at this point, you need to use the definition of the length. Right, because this is the length. The length of this would be V6W, and then you repeat it, minus 6W like this. And then what do you do?
Yes, separate again.
You separate, right? When you separate, the way you separate them, like we said before, then you need to separate them in order. You treat this one as one vector and then expand. Okay, if you treat this one as one vector, you would then say, for instance, you have V, then the V minus 6W, you keep them. And then now you can put a plus here. Okay, you can put minuses if you want. And then we have minus 6W, and then the V minus 6W, keep them. Next. Okay, you have V. And then you have plus V minus 6W. Okay, so you expand like that. And then you come to this one here, minus 6WV. And then plus minus 6W minus 6W, like this. Okay, and then you have exactly this here. Okay, like so. Now, let us check this out. Now, to check this out, the couple of things you need to do. Like, you'd have the inner product of V with itself, right? This one is the same as what? It's the same as the length squared.
Oh, yeah.
Right. So it would be the same as the length of V squared. And then this one here, you can take out the 6. And
Yes.
then it's going to be exactly VW. And then here you can take out the -6, and then you have, okay, and you have this here, and you have that. So your, and we have these. Okay, let's see now. Where are we? We're here. We take out the -6, and then you have the V, the WV. And then here you take out the 6 and 6, and it becomes what? Plus 36, and you have WW, like this. So, okay, and WW we
Oh,
know.
you say 6 squared, right?
Yes, then
Okay.
yeah,
Because
there's
you
6 squared. Well
removed
done.
all of them.
Yeah, all
Okay, yeah.
well done.
Okay, no, it
6
makes
squared
sense.
because we remove, yeah, we're removing both of them. Right. So
Okay.
yeah, here I wanted to say then you have the 6 and then you have the W like that. Right. So obviously, hang on, I need to write it well with the -6. Okay, yeah, I just because the W was a bit too tiny to see. Something like that. Okay, right. So you get this now, and at this point you pull out both of the minus, -6, and you get that. Now let's look at this. Okay, now if you look at the length of V, right? So the length of V is going to be 3 squared. Right. So now this VW is 2. Well done. So this is going to be 6 and 2 here, -6, and then there is WV.
Yeah, that's what I was asking.
Okay.
Is it the same thing?
Okay, yeah, definitely. So obviously, it's the same thing in the real vector space.
Okay.
Okay, but in the complex vector space is not the
complex.
same. Yeah, okay,
Okay.
I'll give you because I'll tell you. There's something I'm going to mention very quickly in line with that. Right, there's something I'm going to mention. Okay, there's something I'm going to mention in line with this. Right, in like in a split second, just now. Okay, there's something I want to mention in line with the with what I'm saying here. Because yeah, that's why you're asking, because you already saw it. With me, I'm doing this question for the first time ever in my life. Okay, but now I want to discuss that because in the real, which is the case here, so it's the same thing, but in the complex, it's not the same. But I'm gonna state here the most general rule for this. Okay, this is called the conjugate symmetry. There is something we call conjugate. We call it conjugate symmetry. What is conjugate symmetry? Okay, in mathematics, we are taught that the inner product of UV is equal to the complex conjugate of the inner product of VU. Okay, I mean this is the most general rule for that. Okay, so okay, there are very advanced books sometimes on linear algebra, because you see the way we are taught, sometimes we're not taught very nicely at the elementary levels. Because maybe that's the thing, because the lecturers just teach us the real vector spaces because they think if you know the real vector spaces, then you can just use your knowledge to learn complex, because the complex is a bit more general. But now there are some books that are used at second year. So there are some books that are used at second year. So yeah, okay. This is called conjugate symmetry. This, and this is true for all vectors U and V in the vector space, or in the inner product space. Okay, so this is the general law. But what then is called conjugate symmetry? But these things, in other words, in general, in the complex case, it's not the same. When you want to reverse the order, you put a bar on top. When you have UV, and if you write VU, you put a bar on top. But then in the real inner product space, then the bar, because what is a complex conjugate? Well, when you're doing complex numbers at first year, you take the complex conjugate of this, A plus IB, it becomes minus like this. But what about if you're dealing with a real number, a real number that is just A alone? What is the complex conjugate of that? It's just A, So that is the reason. So here, this is the same in the real vector space. So that now, you are dealing with the this is going to be WV is the same as VW, which is 2. Right, and then we have 36, and then now we have W, the inner product of WW, which is the same as the length squared, right, which is 4 squared, like so, just 4 squared. Okay, now let us look at exactly what this means. Let us look at what this means, my goodness Lord. Okay, good.
Okay.
Let's look at what this means. So we just need to simplify these things. So now, if you look at this very, very carefully, right, now the 3 squared is a 9. Okay, now here you then have these two guys here, which is minus 12 minus 12, minus 24. Right, and then now we have 36 by, okay, not very nice numbers, 36 by 16. Okay, we're gonna use a calculator just to confirm our answer. But yeah, but in mathematics sometimes we're not very much interested in the numerical answers. We're interested in the logic and the principles. Once obvious at this point you get the logic, then you go on. Okay, so
Okay.
right, let us use this calculator to actually do the calculation. So we're gonna have here a 9 minus 24 plus 36 times 16. And this is actually 500 and what? And 61. Right, so it's actually 561 square root of that. And obviously that sort of becomes the answer. And obviously you can think about the following. If you look at the calculator, you can think about the following. If you then say square root of the answer 561, okay, getting this one, which is okay, remember it's yeah, it's doing it's one thing there. Okay, but you can see that it's quite it's going to be quite a thing. It's going to be quite a decimal. So anyhow, but this is the length, and now you must say this is the answer units. Okay, this is the answer units. Right, so we continue. Right, we continue. Let's move to the next question, please. Right, so move to the next question. Okay, I wanted to speak about the properties of the inner product here. Okay, it's something that, I know that you possibly know very, very well. And, okay, now let us speak about the properties of the inner product very shortly. All right, I know that this has been, is there in the study guide, I think. Okay, right, definition, right, definition of what we call the inner product. But I'm going to look at the general definition here. Right, we start by saying an inner product. An inner product on V is a function. Your lecturers can tease you, but normally they don't ask for definitions. They can ask you tomorrow, what is an inner product? Okay, they ask you to, normally they want you to use it because they know the definition is going to be obvious. They want you to use it.
Yeah.
Right, so an inner product on V is a function. So an inner product is a function that takes each what? Each ordered pair. Each ordered pair. Now you deal with the ordered pair here, which is the ordered pair UV of elements of V to a number UV element of F, right, element of F, like this. And you see, this is how we write the F, and has, when this F is a field, and has the following properties. the following properties. There's something we call the positivity. Positivity. What is positivity? Positivity means that the inner product of a vector with itself is always greater or equal to what? It's always greater or equal to 0 for all V in the inner product space. And then there's something we call the definiteness. Definiteness. And the definiteness condition is that if you take the inner product of V with itself, the inner product, when is the inner product? 0. This answers the question.
If
Inner
V
product
is
is 0 if and only if. When is the inner product 0? If
V
and
is
only
0.
if V is well done. If and only if V is a 0 vector. Right.
Yeah.
Then there's something that is called the additivity. Additivity. Right. Something called the additivity in first slot. Right. Additivity in first slot. Right. Now, what is additivity in first slot? So additivity in first slot simply means that you can add in the first slot. Right. So you can have vector U plus vector V, vector W. And this thing here is the same as vector U, vector W, vector V, vector W. And this is true for all U, V, W in V. And then there's something we call the homogeneity. I think I saw the same concept in your material, in the study guide. Right, the homogeneity. Homogeneity. Okay, just to write that a bit clearly there. Right, now the homogeneity, right, homogeneity in first slot. Okay, this would be right. So yeah, but the way I'm looking at things here, these are the properties for complex vector spaces, but then the real follows from this. Right now, the homogeneity in first slot would mean that in the first slot, if you have lambda UV, then there's homogeneity in first slot because you can pull out from the first slot, and this becomes UV like this until this is for all lambda in F and all UV, all vectors UV in the vector space. And then there's something called conjugate symmetry, which we've just spoken about. Conjugate symmetry. Right. What is conjugate symmetry? Conjugate symmetry means that if you have UV, the inner product of U and V, it's the same as the inner product of what? Of V and U, right? The inner product of V and U with the complex conjugate, right? The inner product of V and U with the complex conjugate like this. And this is true for all vectors U and V in the vector space, right? So obviously this is a definition of the inner product, but a couple of things you need to take into account here. We spoke about the positivity, meaning that the inner product itself is sort of non-negative, meaning if you take the inner product with itself, the result is always greater or equal to 0 for all vectors V in V. The definiteness property, right? So the definiteness would mean that the inner product of a vector with itself is 0 when we're dealing with the zero vector. When V is a zero vector, if and only V equals a zero vector. Additivity in first lot. The additivity in first lot, it is the property of expansion. To say now, if you have U, V, and W, then how do you expand this? It becomes U and W, the inner product of U and W plus the inner product of V and W. Now, homogeneity in what? In first lot. The inner product of lambda U and V, you can pull out lambda and then it becomes lambda, the inner product of U and V for all lambda and F and all U, V, and V. Now, the conjugate symmetry, the inner product of U and V, it is actually exactly the same as the inner product, right? The inner product of V and U. So if you change the order, you put a complex conjugate over the reversed order for all vectors. So yeah, this is sort of obviously what you need to take into account there, and it's something that it's very important. As a deduction, what would we deduce? For example, from this particular additivity in first lot property, what about if you have U and then V and W? What then do we get?
UV.
So it's going to be
Inner product
UV.
of UV.
Yeah.
Plus
Plus UW.
UW. Yeah.
Well done. Okay, and this is true. Sometimes you can use this notation. You say it is true for all UV in what?
In
In
V.
V. Okay, yeah, the inner product space. All right, so yeah, we had a chance to figure out the properties of the inner product there. Okay, let's move on to other things. Once again, this thing is recorded, so you'll have a chance to have that. Okay, you looked at 5. Which other question you'd like us to look at?
Can we look at 6 first? And then with 5, I just have a particular question. The one which says we should find the subspace, the span.
Okay,
And the
okay. So you continue.
yeah, it's B.
It's B. Oh, is it 5B?
Oh, but no, I can do it. Okay, it's fine.
Which one you like us to do?
Can we do question 6 first?
Okay, that's fine. Let's look at 6. Okay, let's look at 6. Let's look at 6. Well, we're looking at 6 just now. And there's this other student who doesn't sleep. He sends me messages like you can't believe. So now I'm moving to 6, but now he's not breathing. He's sending me 100 messages and expects me to reply. And he expects me to reply
You have a class
now.
with him.
You're
You're supposed to meet him now.
Not exactly, but it's just that we mostly do all the modules because it does mostly the physics and the math. Yeah, it does the physics and math and chemistry. So normally we do all the modules together. So each time he sees a small challenge, then he's up. He sends me 100 messages. Okay, never mind. Okay, right. So we continue then right now. Right. So you wanted us to go to 6. Okay. Yeah. Right. We're moving to 6. All right. Now this is question 6. Question 6 is long, but I want to give you a hint about
how to approach these questions.
These long questions. You know, there is a hint. These long questions, like let's read the statement of this theorem. Okay. Also, the question says, read the theorem and proof given below, and answer the questions that follow. If a vector space V has a basis with n elements, then any set of vectors in V with fewer than n elements cannot span V. Okay, so what is this? This story is it's a story about 2 things. And I must mention that these long questions that they ask all the time, they're about linear independence and basis, that's all. So, and this story, they've given you this story here, but now you are dealing with the basis. Right? So if a vector space, and obviously always they mention vector spaces in the long questions, they mention bases, like in the one we did last time, the long question, it was eigenvectors that are linearly independent all the time. You know, and there was a presented proof about eigenvectors that are always linearly independent, and therefore you had to deal with linear independence. you know.
Mm.
So these are the kinds of things, therefore, that become extremely, extremely important. Now, if you look at these, then you need to therefore be in a position to then say, these kinds of things remain extremely, extremely important. Okay, there's something more I want to mention here, because here they're effectively saying that if a vector space V has a basis with n elements, okay, now, okay, all right, okay, we'll continue. So if a vector space V has a basis with n elements, what does it mean? Then n is set. So now we are dealing with a basis with n elements. A basis with n elements, it means that you have a set that is linearly independent, but that is how many elements? That is n elements. Okay, then any set of vectors in V with fewer than n elements cannot span V. Or obviously cannot span V, cannot generate V. Okay, the word span is the word generate. Sometimes obviously the word span is just the most popular in linear algebra than the word generate, you know. Instead of saying it's a generating set, the English people love the word span. And yeah, it is. And I feel that the word span is not, the word generate is more meaningful sometimes, the word span, but obviously the word span is used in the context of really saying it means to generate as well. So they're like synonyms in this case, right? So the proof, let's look at the proof. Okay, you look at the proof. I don't want to spend a lot of hours on the proof, but I want us to look at the questions and just to see what part of the proof we need to analyze here. Okay, and also this is your key. The proof is already done. Don't waste time on the proof because you're under exam, conditions, right? So now, if you read the proof too much first, I feel that you're gonna waste time. Now, because the proof is already done, you don't need to do it again. But you need to say, explain where the equations at 4 come from. Then you go. Okay? Then you go. Then these equations, where do these equations come from? Right. Now, you can quickly browse through. Okay, we started with what? You started with a set with n vectors. U1, U2, up to UN, a basis for V. Indeed, it is consistent with the fact that you have a vector space V with n elements, and these are n vectors. Right, and it's a basis. Because it's a basis, it means that this set is linearly independent. Then any set with fewer than that. So now you need to say any set with fewer than n elements. So you take fewer, k. Now you then say the S primed is gonna be a set that is fewer elements, k of the vectors, such that k is smaller than n. Okay, so obviously that the set S primed is fewer elements. Be a subset of V with k less than n. Okay, let us assume that S primed spans V. Okay. So now this is very, very interesting. So for a contradiction, now, okay, you look at that, and then you look at the at the end here. Right. Right. So you have that. Right. And then now for a contradiction, sort of, you obviously would assume sort of the opposite here. All right. But you assume that it spans V and possibly run into some issues because we know that it cannot span. And then now you are actually assuming it spans. Right? So let this one be a subset of that. Let us assume that S prime spans V. Okay, we can write. Because it spans V, what does it mean to say it spans V? It means that every element,
vector.
yes, every vector of V, it generates V. It produces all the vectors in V. Because it generates V, it spans V, it means every vector in V can be written as a linear combination of the elements in S primed. So the S primed has how many elements? Has the K elements. So now you take the K elements and then you multiply them by what? By scalars. Okay, these scalars, they're not just scalars, but they give them these particular names. So obviously you can see that S has how many as N? So you take U1, you write this like a combination of this. U2 is a linear combination of this, and up to UN is a linear combination of that. So obviously, the question then is that we are back to then answer the question there to say, where are these equations coming from? Right, and these equations, once again, the equations that are emanating from the fact that our assumption that you assumed that S prime spans V. Right. Now, our assumption that S prime spans V, right? So, in other words, yes, that is exactly the thing here. So, we assumed that S prime spans V. And therefore, it means that for every vector in V, and hence every vector in S, the U1, U2, UN can be written as a linear combination of the vectors in S prime. So that is exactly what we say here. So we then say that it makes sense to then say that if you have the V1, V2, Vn, okay, so we have the basis there that is given. If this one spans what? Up to Vk, I want to take them up to Vk. Okay, so yeah, we can write it, let's write properly. Right, we can say that if, okay, this one we called it S primed. Okay, we called it S primed, which is up to Vk. Okay, so we take this one up to Vk. Right, so if this one spans V by our assumption, okay, spans V by assumption. Right, so if it spans V by assumption, then from the fact that it spans V, it means that, you know, by assumption, then every vector, okay, let's write this one. Yes, then every vector in V, then every vector in V, right, can be written, right, yeah, it doesn't matter. Then every vector in V, don't need to write many things here, can be written, write the keywords, right, can be written as a linear combination, as a linear combination, of what? It's a linear combination of these V's.
The elements.
Yes, of these elements there. So which are the V1, the V2, up to Vk. All right. So this is something that this is where the equations are coming from. Okay. And obviously, and this is where those equations are emanating from. We move to the next point. B. All right, so let's check. Yes, why will the equation at 5 be enough to complete the proof as claimed at 6? Let's check that. Why will the equation at 5 be enough to complete the proof as claimed at 6? Let's check. Right, so why will the equation at 5, which is this one, be enough? Okay, we now show that. Okay, because we got those equations. Then we proceed to then say, we now show that we can find the scalars B1, B2, up to Bn, not all 0, such that this is the case. Okay, and then which will complete the proof. Right, so obviously now let's look at this very carefully, and obviously it's very easy. But now remember that what will complete the proof? And yeah, because our assumption is that we are assuming that S prime spans V. Right. And if S prime spans V, obviously it means that you can write that linear combination. And in the end, we then say that then any set of vectors in V with fewer than n elements cannot span V. So obviously, if you look at the fact that we now show that we can find scalars B1 up to Bn such that this equals 0, and which will complete the proof. Right. So now, if you look at this very carefully, you need to think of the fact that okay, now I want to mention something. Not all 0. We can find scalars not all 0. Remember that we are dealing with bases here. And in the case of a basis is linearly independent, meaning the scalars must all be 0.
0, yeah.
They must all be 0. But you need to note that we said that if V is a vector space and it has a basis with how many elements? N elements. The basis with n elements would mean that all the scalars are 0. So we must find that all the scalars are what? Are 0. So now, if not all of these are 0, it means that we therefore have a contradiction, right? Because if we have n vectors, we said let S be a basis for V. A basis for V, it means that this set is linearly independent, and it means that if you write a linear combination, every scalar must be 0 because it's a basis. It's a basis. So now, and this, it will complete the proof that if we assume that we have fewer vectors, then we run into a contradiction. And also, we're saying we now show that we can find scalars not all 0, such that that is the case. Obviously, this becomes a contradiction. Okay, there are many things you can say there, but let's write the following. Right, let's say that at this point, this is actually because, right, it is because the fifth equation, right, the fifth equation is a contradiction. And we want to discuss why it is a contradiction, as we've just mentioned. Right, it's a contradiction to the fact that, right, it's a contradiction to the fact that U1, U2, UN, because they are from a basis, these are linearly independent. Yes, because they are from a basis, they are independent. And therefore, because once again, and now it will be problematic to then say this, not all the scalars are 0. But then, as said already, so it will therefore obviously complete the proof then to then say our assumption is faulty. Our assumption is faulty because it's a contradiction. It goes against the norm. What is the norm? The norm would be that a basis, all scalars should be 0 in a basis. You get the point. But now we would find that not all these scalars are what? Are 0. Yes, and obviously that would mean a contradiction. Move to the next point. Right, explain where the equation at 7 comes from. Let's check. Explain where the equation at 7 comes from. Right, this one. Explain where the equation at 7 comes from. Okay, right, let's see. Right, so now if you look at this, okay, so let this one be equal to 0. This means that you have this particular thing. Then there is an equation. Okay, that's very interesting because these things are, this is like a sum. It's this plus this plus this plus this plus this plus this. And then you are adding. Okay, because it's B1, and then it's B1. Okay, so it's B1, A11, B1, A12, B1, A1K. Then B2, A21, B2, A22, B2, A2K. And then you go on to Bn. Right. So obviously you can see that equation. It's coming from here, because now if you look at these, there's gonna be B1, and then if you have this B1, then you substitute all these. Okay, and this is like K terms. Right. So if you substitute this, it's gonna be B1 A11, B1 A11, and then there's gonna be B1 A12, B1, the last one, A1K, B2 A21, okay, and so on and so forth. So obviously, now they're saying explain where this equation at 7 comes from. Okay, so it comes from that. It comes from substitution. Substitution of equation 4, of all these equations 4 into what? Into this equation 5. So we substituted this U1 here, and then the U2 there, and so on and so forth. So it comes from the substitutions. You get the point, right? And that is what we actually, obviously, we say there. So if you take the U1, you put the place of U1, the U2, you put it there, and up to the UN. So we then say, we're able to say that, right, we're able to say that we substitute, right, we substitute U1, okay, you can put U2, we substitute those U's, okay, we substitute these U's, we substitute this U1 into there, U2 into that. So substitute U1, U2 up to UN into the equation 5. Right, so that's what we say. So we substitute U1, U2, and then up to what? Up to UN in 5. Right, by what? By the right, by the right hand sides, by the right hand sides of 4. Anyway, yeah, you substitute all the equations in 5. Right, we substitute the U1, U2 that in 5. Right, so you put all these U1, U2 into equation 5, and that is where the equation at 7 comes from. Let's move to the next point. Right, why does the system of equations at 9 have non-trivial solutions? Okay, let's check that one. Why does the system of equations at 9 have non-trivial solutions? Let's check. Where is 9? Right, so 9 is this one. Why does this system have, because we're saying, but this system of equations clearly has non-trivial solutions for B1, B2, so for B1, B2 up to Pn. So the proof is finished. So we're saying, why does it have non-trivial solutions? Okay, for instance, you look at this. We will have scalars B1, B2 up to Pn as needed, as long as we can find a non-trivial solution of the following system of what? Of equations. But also, if you look at the fact that we actually made an assumption that we assumed that the S prime here when K is less than N, right? So we actually assumed that S primed is a subset of V with K less than N. And we then said we assume that S prime does what? Spans V.
Spans V.
Right. So because this K is less than N, we know very well that for N vectors, we have a trivial solution. Right. So obviously for K less than N, we would actually have a homogeneous system with K less than N symbols And because of that, it is necessarily having non-trivial solutions. And we actually would say the following, right? We can say because, that's fine. We can write like that in many ways. Okay, because all the time for the basis, we write a homogeneous thing. Always for the basis, we equate to what? We equate to 0. So okay, so because we equate it to 0, then we have a homogeneous system. Right, so and you can say that because the system is a what? It's a homogeneous, meaning it's equal to 0. Right, it's a homogeneous system. Right, it's a homogeneous system. Right, it's a homogeneous system with n variables. With n variables and k equations. This is very important. So we are dealing with a system. Okay, this system is a homogeneous system with n variables and k equations, where k is less than n. All right, so what are we effectively saying here in a nutshell? Which one is bigger? N is bigger than k.
Is bigger than k.
So in other words, it means that if you have more variables than the equations. So if you have more variables than the equations, it means that, for example, you can have like x plus y plus z. It's one case and it's homogeneous, so it's equal to 0. And then here we might have 2x minus y plus 3z equals 0. So you are having like more variables than the equations. Here the variables are 3 and the equations are 2. Right. And as a consequence, then we then say we have what? Non-trivial solutions.
Non-trivial.
Yes, we have non-trivial what? Solutions. Meaning that potentially here we end up finding ourselves having like infinitely many solutions, you know, but we do not have like unique solutions, because those unique solutions would require us to have like 3 equations. The number of the equations must be equal to the number of the unknowns. Okay, let's move to the next point. Okay, I'm seeing the time. We lost you.
Okay.
Okay, we are still here, right?
Oh, okay.
Thank you so much. Yeah, okay. I think that the network just went.
Okay.
And then it's just restoring. Just 1 minute. I think that it's something with the general network. Yeah, okay. It just went, but it's restoring now. Okay, so it is restoring. It is restoring, so please, apologies. So it might do. See, now it's doing strange things here. It's doing strange things. Let's see. Okay, I might need to reconnect. Okay, let's see. Okay. It might be doing, it's like it's doing 2 videos. Wait a minute. Okay, I'll just be with you now. There's something I'm trying to sort out. Are you able to see the screen? Yes.
Yeah, I can see.
Okay, good. I'm trying to verify because I think the network just was disturbed a little bit. You never know. Maybe because of the fact that, you know, we had a power issue earlier on, something very strange. We did not have load shedding for a long time. But when we're up at 5 a.m., there was just no power in the whole area. And, you know, we're like, how come? And then now we're planned for 10 a.m. I was so disorganized. My phone was off in the early hours of the morning. I had to charge it quickly, etc. And so it was terrible. Okay, state whether each of the following two statements is true or false, giving brief reasons for your answers. If V is a vector space, R spans V, and R has M elements, then any subset of V with fewer than M elements cannot span V. Okay, so state whether each of the following is true or false. Okay, so let us look at this one here and think about it and see. Right. So we read again. If V is a vector space, R spans V. So there's a set of vectors that spans V. There's a set of vectors that like generates V. And this set of vectors can like have like n vectors, etc., that like generates the whole of V. Meaning every vector in V can represent a linear combination of those elements there. And R has M elements. Okay, they're telling us that this R spans V, generates V, yet it has M elements. Okay, so then any subset of V with fewer than M elements cannot span V. Okay, so let us look at these here. Okay, let us look at these here as a matter of fact. Right. We see now this one is a very interesting one. And it hinges on two things in general before you even start arguing here. The examiner is using the word span, and then we have the word basis. Span can have any elements. So, but bases have fixed numbers of elements. So if you then say, then any subset of V with fewer than M elements cannot span V. Right, so obviously, a subset of V with fewer than elements, with fewer than N elements, fewer than M elements can span V. Okay, I want to mention that. Obviously, we make mention of the fact that this claim itself is false. Okay, this is false. Why? Okay, a typical example would be that, okay, I'm gonna follow here. Obviously, if you let V be a two-dimensional Euclidean space, you can give other examples. Right, we can let V be a two-dimensional Euclidean space. Okay, because now, why are we doing this? Because this is false, so there's no proof. You can just use numbers, an example, a counterexample, we call it. Right, you can use a counterexample. Let V be R2 and R. Now, you can take R to be, for example, a what? You can take R to be a set that has a set that is what? That is more vectors. That is M vectors or 3 vectors, suppose. And then we then say, right, and now how many elements do we need to span V, to span R2, to generate R2? We need 2 vectors only. Okay, but now we can take this one that is 3 vectors. And then we go on to then say, let that be the case, and we make mention of the fact that R generates V or spans V. But if you look at this particular set, R primed, which is the basis with the required number, but smaller Right. I think just a slight interruption. You're still here, dear, right?
Yeah.
I must apologize that I think that it's a slight interruption. I think the network is a little bit unstable.
Okay.
So okay, yeah. You're fine now.
Yeah.
Okay, good. Yeah, it's a bit it's yeah. Okay, yeah, it's okay because it's popping and are you able to see the screen?
Yeah, I just see physics. I can't see the
You can't see
the
the thing you're
presentation.
writing. Yeah, that's the thing.
Yeah.
Yeah. Okay. Good. Yeah, that's what I want because it is just okay. I'm sorry, just the network now. It's it's making the things to act up, but I'm sure that it is very sporadic. It's strange that I'm seeing that. Okay, yeah, okay. I can see that you're seeing I love physics, so I need to share. Right. Need to share, and then let me see.
Yeah, I can see now.
You're able to see.
Hmm.
Okay, well done. Yeah, just 1 minute because there are too many things I'm trying to operate here. Let me see. Okay, just 1 second. I'm trying to set the things properly. Okay, because it's acting up. It's the network. I'm just yeah. It's just one of those odd times. I don't know. Just happening. You're able to see now.
Yeah.
All right. So we're then saying if V is a vector space and R spans V and R is M elements. Where was I writing now? Let me see. Okay, we're here. Right. So we take R to have like 3 elements, and this is like M. And then now, if V, okay, any subset of V with fewer than M elements cannot span V. Right. So you can take this one, for instance, with 2 elements. Right. So now if you have 2 elements here, it has 2 elements and still spans V. Okay, so obviously we're looking at the fact that you really can have a set that has redundant elements, more elements, some of which are redundant. Okay, because this example of R2, the basis must have 2 elements because R2 is of dimension 2 by definition. Okay, so R2 has dimension 2, but now if you put 3 elements, so you can have M elements, then any subset of V with fewer than M elements, so you take now a subset that is fewer than 3 elements, yet this one still spans V. It still spans V. So in other words, this claim itself is false because these bases can be extended. Bases can be extended, in which case you can have more elements. Right. So obviously we're not restricted to a given number. Bases can be extended, so you can have 2 elements here, you can extend to have 1. Okay, if you have like 3 elements here, and we then say we have V a vector space and R spans V, and R has M elements. In this case, R has 3 elements. Then any subset of V with fewer than M elements cannot span V. Well, we have 2 elements here and it still spans V. Because for it to span V, we just need 2 elements minimum. 2 elements minimum to span V, to generate V. And this kind of basis, we call it the canonical basis. Okay, just canonical basis. Okay, it's like the one we use, or you can write like 0, 1, 1, 0, or the other way around. Okay, so this is the kind of basis we use to generate, or you can write for R3, it would be, sometimes I like starting with the ones here, 0, 1, 0, 0, 0, 1. Okay, this will be an example of a canonical basis, or what we call the natural basis in the Euclidean spaces. Right, but now you're able to see, therefore, that these natural bases would be such that it generates, or it actually such that it still spans V. It still spans V. We have 3 elements, but it spans V. We have 2 elements, it spans V. How do you know? Because R2 just needs 2 or more elements. Okay, then obviously 2 or more elements, then like this one is the same as this. Okay, this is the same as this. So obviously in the next case, because it's like, is this one multiplied by 2? So it's a redundant element, it's superfluous. We can cross it out and then be left with the first 2. Or we can cross this one out and be left with 2, 0. But we don't like 2, 0 because natural bases have zeros and ones only. So we can just take the zeros and ones only and throw away the 2, 0. But we can also cut out the 1, 0 and have the 2, 0 and that. But obviously, this is another basis, so that will also generate. So my point is now the 0, 1, 2, 0 would also be able to generate what? Also be able to generate or spans V as well. You can take this one, you can take this one. They generate V. They generate V. So in other words, this claim is obviously a false claim. Okay, we're trying to discuss. Okay, but now what are these things about? All these things we're doing here, what are these things about? They're about linear independence and basis and the span. That's all. Linear independence, all the scalars are 0, the scalars are not 0, or not all the scalars are 0, and then the basis and the span. That is everything about these proofs they bring. So they're not proofs that are from space, from Jupiter and strange and things. State whether each of the following are 2 statements is true or false, giving brief reasons for your answer. If V is a vector space, R is an independent subset of V. Okay. So you have a vector space, and R is an independent subset of V. Okay, that is what I'm saying. That everything here is about linear independence. So here they're telling you that R is just a linearly independent what? Subset of V. And R has M elements. So we have a linearly independent subset that is M elements. Then any subset of V with fewer than M elements cannot obviously span V. Right. So this is true, because you already have a linearly independent subset. You see, in the previous case, it was just a set. It was just a subset of V. But R is already linearly independent, because you see, in this example, this set here, R spans V and has M elements. In each case, therefore, this R has 3 elements in our counterexample, and obviously, but it is not linearly independent, this. Okay, linearly independent would mean that you would need the correct number. In R2, linearly independent would need 2. You need 2 vectors because of the dimension of the vector space R2. All right, so now, I'm trying to therefore compare the two, or contrast the two, to then say, now, here we're saying R is an independent. So this one is already linearly independent. Linearly independent means what? Right, linearly independent, you can't remove the things. Linearly independent, you can't remove. But linearly independent, you can add. Okay, this is very important. Linearly independent sets you can increase the size, but you can't deplete. You can't remove. Okay, so now, and there's a theorem obviously that says that. So now, we argue that obviously this is true. It is true that if you have a linear independent set, then any subset of V with fewer than M elements cannot span V. Right, so this is exactly what we have. Right, this is true. Why? You can then say that here, if V has an independent set, with M elements. With M elements. Then any set of vectors any set of vectors in V with fewer, we shall discuss this statement we're writing here, with fewer than M elements, shall discuss and justify the sense in this, cannot span V. Okay, I mean, it is based on the fact that if you have a linear independent set, then you can't reduce, you can't have less elements. You can't have fewer elements than there are in the linear independent set. And it's enough to say that. But now we're saying here, this obviously is true. If V has an independent set with M elements, then any set of vectors in V with fewer than M elements cannot span V. It's exactly that. So if you have a linear independent set, in other words, if V has a linearly independent set, because V is the vector space with all the vectors, and then now if you are to take a subset of V that is linearly independent, then with M elements, the independent M elements, then any subset of V with fewer than M elements cannot span V. It can't span it because V is already spanned by a set with M elements that is linearly independent. A set with this linearly independent cannot be made smaller in terms of having fewer elements. Okay, so that is something that is important. It's something that is important. Okay, now we are saying if V has an independent subset, you can call it. Okay, because now the way it has been written here. So V is an independent subset. Right, so V is a subset, R is an independent subset of V. So if V is an independent subset, okay, I can write properly here. V has an independent subset, right, as an independent subset with M elements, then any set of vectors in V with fewer than M elements cannot span V. Because why? Is they independent, then we can't have fewer elements, because the one with fewer elements cannot span V. Because the one that is spanning V is linear independent, then we can't reduce the elements. Think about it. But yeah, that's sort of the point that must be noted there. So if you have a linear independent set, you can't cut down the elements. You can't cut down.
Okay.
Okay. Because if you cut down, then it cannot span V. Because V is already spanned, is already generated by a linear independent set. Linear independent set has sort of the correct number of elements you need. Okay, so you can't go below that. Okay, now if you look at this, okay, prove or disprove each of the following statements. Let S now, S is having 4 elements. This is the same as the one you looked at last time. It had what? Some what do you call those? The eigenvectors. It had eigenvectors instead of the one you looked at last time. So it is very similar, but let's just see what they say here. Right, let S have the 4. That one had like 3 eigenvectors, but now here this one is 4 vectors. Right, a subset of a vector space with 4, not a linear combination. 4 with V4, not a linear combination of the other vectors in S. Then S is a linear independent set if and only if V1, V2, V3 is a linear independent set. Okay, so this is then what we have here. Okay, let S is a set with 4 vectors. And we're saying let S be the set with 4 vectors such that it is a subset of a vector space V with V4, not a linear combination of the other vectors. Okay. So now this is very important. V4, not a linear combination of the other vectors. So what does it mean about linear independence? We'll discuss that. Then S is linear. This is what then it comes for. So now there is an inference about linear dependence. Then S is a linearly dependent set if and only if V1, V2, V3 is linearly a linearly dependent set. Let's look at these and analyze these together. The conclusion is then, which is what we need to justify ourselves, prove what is proof. Then S is a linearly dependent set if and only if the V1, V2, V3 is a linearly dependent set. Okay, so obviously look at these and you think of this. So, but first things first, because we are told that V4 is not a linear combination of the vectors there, right? It is a true statement that then S is a linearly dependent set with four vectors. The four vectors themselves are linearly dependent if and only if the V1, V2, V3 is a linearly dependent set. Okay, right, so let us analyze the fact that S is a linearly dependent set. So the four vectors are linearly dependent if and only if the three vectors themselves form a linearly dependent set. Okay. But also we need to take note of the fact that we have the four vectors, but with these four vectors, we have that these four vectors themselves, they form a subset of a vector space with V4, not a linear combination of the other vectors in S. Okay, I want to look at a special case here. I'm not saying this is the proof yet, but if V4 were to be a linear combination of the other vectors, so it would mean therefore that V4 could be written as AV1, okay, A1, V1, A2, V2, like A3, V3. I mean, this would mean V4 is a linear combination of the other vectors. But now we're saying V4 is not a linear combination of the other vectors in S. So this is not the case. Okay. Because if this were to be the case, what would it mean? It would mean that V4 can be written like this. And it would mean what? It would mean, therefore, if you write the things differently, like AV1, you can rearrange these things. And then you have A2V2, A3V3, minus V4 would be 0. So that would mean that you'd have a scalar that is not 0 in this linear relation, such that you have a homogeneous system, but not all the scalars are 0. And because not all the scalars are 0, it would mean, therefore, you can come to this observation from the fact that V4 is not a linear combination of the other vectors. So obviously, you would have this. V4 is not a linear combination of that. And you'd have that. Then S is actually a linearly dependent set. So now we are dealing with set. So these things here, because S has 4 elements, so you have like 4 vectors. So S linearly dependent set, if and only if now the 3 vectors themselves form a linearly dependent set. So we're then saying if ever V4 were to be a linear combination of this, it would actually therefore imply that you would write it like this, and that would mean the set S would be linearly dependent if V4 were to be a linear combination of that. So I want us to obviously prove this. But how do you prove this, and how do you make sure you are on point? Because there are just too many things you can say here all the time. And now there are like lots of things. Right. But now I want us to look at the fact that then S is linearly dependent, if and only if. So the 4 vectors are linearly dependent, if and only if the 3 vectors actually form a linearly dependent set. Okay, so this obviously is a very, very important observation. But now there's more we can say. But first things first, we take note of the fact that this generally is a true statement, right? Then S is the linearly dependent set if and only if V1, V2, V3 is a linearly dependent set. Okay, right. Let us actually look at how we can prove these. But there are a couple of ways, obviously, you can use to reason this out. But once again, we actually make the observation that the way your lecturer, recommends you answer this question is whether you prove or you disprove. You need to indicate that in the beginning of your writing. And you need to then say, first, this is true or this is false, so that the lecturer will know that if it's true, then you are writing a proof. If it's false, then you are doing what? You are actually disproving. You're getting a counterexample. So this becomes a very logical way to reason this out. And now, the couple of ways then. So we can then say, you can say let V1, V2, V3. Right, so let V1, V2, V3 be linearly dependent. So let V1, V2, V3 be linearly dependent. So what are we doing here? We are starting from the end of this, because this is like if and only if. So we're starting from the end. So we're starting with these 3 vectors that are such that they form a linearly dependent set. Then S that has 4 vectors, V3, V4 is linearly dependent. Right, is linearly dependent. Right, so let us analyze these together. And we're saying this is trivial, so it's obvious. Okay, obviously one way of saying something is trivial is saying it's obvious. Okay, let us elaborate on why this is the case, because we're writing these sets and these sets do not make any meaning sometimes. Right. So now what you need to do is to say that if you start with these and you are saying linearly dependent, so you write A1 V1, A2 V2, A3 V3. Right, so you have A1 V1, A2 V2, A3 V3 is equal to what? Is equal to 0. Okay, because it's linearly dependent, but you're saying not all A1, A2, A3 are what? Are 0. Okay, you can write like that. Okay, now you're starting with this one is linearly dependent. Then now, if you come to you include the fourth vector. You include the fourth vector. So you can then say there is A1, V1, A2, V2, A3, V3, but you're told that V4 is not a linear combination of the other vectors in S. Right. So even if these are not all 0, so you can add A4, V4. But since these ones are not all 0, even if you choose A4 to be 0, not all these scalars would be 0. So, and now, because of that, it is then you're saying not all A1, A2, A3, A4 are 0. Okay, why are we doing these things? We're saying that if you start with a few elements that form a linearly dependent set, even if you extend like this, you have linearly dependent set here. Okay, right. And with this, here, we've said, we've proven this in reverse. We have V1, V2, V3 linear dependent, then we have that. So this means that, and this means that S is linearly dependent also. We started with V1, V2, V3, and then we got that S is linearly what? It's linearly dependent. Right. So now we proved. So now we proved what? We proved this direction, because if and only if he is like in both directions, right? So we proved the reverse. We started from this and we proved the reverse. Let us prove the forward implication. So now, if you want to prove the forward implication, what do you do? Now, suppose that, right? Now, suppose that, now we want to prove forward. We start with S linearly what? Dependent. Suppose that S with the vectors V1, V2, V3, V4, right, is linearly dependent. Is linearly dependent. Now you suppose that S equals this is linearly dependent. Because it is linear, so you start with S is linearly dependent. Then you want to prove that these fewer ones would also be linearly dependent. Because it's linearly dependent, then there exists lambda 1, lambda 2, lambda 3, lambda 4, not all what? Not all 0. Not all 0, such that you can write lambda 1, V1, lambda 2, V2, lambda 3, V3, lambda 4, V4 is 0. Okay, yeah, you can call this asterisk, star. Right, so there exist those lambdas, not all 0, such that this is the case. Because why? Because we're saying this one is linear dependent, so you have that this is possible, but not all the scalars are 0 because of the linear dependence. Now we can then say, we argue here because we want to reduce these 4 vectors to 3. So now we want to reduce, so we want to look at the case where we can have a 0 term here. So, and to do that, we're saying if lambda 4, for argument's sake, is not 0, then V4 is a linear combination. Is a linear combination of V1, V2, V3, which, okay, if lambda 4 is not 0, then V4, if lambda 4 is not 0, then V4 is the linear combination of V1, V2, V3, which does not hold by assumption. Which does not hold by assumption because V4 is not a linear combination of the vectors in S. Hence, we're told that V4 is not a linear combination. Now, if we want to make it a linear combination, then we're going against the hypothesis there. Hence, lambda 4 must be 0. It follows. It follows from star. It follows from star that there exists lambda 1, lambda 2, lambda 3, not all 0, such that lambda 1 V1, lambda 2 V2, lambda 3 V3 is equal to 0. Okay, so it follows from star that there exist, right? So there exist those lambda values that there exists lambda 1, lambda 2, lambda 3, not all 0, such that this is the case. Okay. Okay.
Yeah.
That is if we take lambda 4 to be 0. If so, in other words, hence lambda 4 is 0. If lambda 4 is 0, then we have 3 summands. And with the 3 summands, then this is equal to 0. Hence V1, V2, V3 is linearly what?
Dependent.
It's linearly dependent. It's linearly dependent. Okay, so to prove this, I proved it in 2 ways. We took first, if the 3, so we proved it because if you need to prove an if and only if statement, because if and only if it's in both directions, you decided to start from the end and deduce the premise. You start from the conclusion. And so we started from the conclusion and we then say, we assume that V1, V2, V3, they form a linearly dependent set, or this is a linearly dependent set. And then we got to the fact that S is linearly what? Dependent. From fewer vectors, we extended that to 4 vectors, and we got that the 4 vectors themselves become what? Linearly dependent, because even here, not all the A1, A2, A3 with 0 when with the 3, even if we add just one more here, would have still that the A1, A2, A3 are not all 0.
Okay.
Then now the because the if and only if is in both directions, then obviously now proving the forward implication was a bit more effort, because we then said, okay, we start with the set S that has 4 elements, and now we have the 4 elements, meaning we can write we have 4 scalars, we can write this particular linear combination. But then now we argue that we want to reduce these 4 vectors to 3 vectors. So one case is to look at the fact that this scalar can be 0, lambda 4, but let's look at the case where lambda 4 is not 0. If lambda 4 is not 0, then we can make V4 the subject of the equation. And now we can, if we solve for V4, it would mean that V4 is a linear combination, but this is saying V4 is not a linear combination. You see, the fact that if we assume here that lambda 4 is not 0, it would mean, therefore, that V4 is minus 1 over lambda 4, lambda, I mean, you solve like this. Okay, because this lambda is not 0, then you can make V4 the subject, yeah, and do this. Right? If you make V4 the subject, then you solve for V4, you transpose this V4, and then you divide everything. Right? So you divide by the lambda 4 because lambda 4 is not 0. And then you're gonna have like lambda 1 V1 plus lambda 2 V2, and then plus lambda 3 V3. Okay, right. So obviously we're doing this now. We are making V4 the subject. And now, if you say lambda 4 is not 0, then we can divide by making V4 the subject. But that makes V4 a linear combination of the vectors like that. And this, by assumption, it's not. And V4 is a linear combination of the vectors, which does not hold by the assumption. And therefore, it means that saying V4 is not 0, it's not correct because it doesn't satisfy the assumption, meaning hence V4 must be 0. Rather, lambda 4 must be 0, excuse. Lambda 4 must be 0. Now, if lambda 4 is 0, then here lambda 4 is 0, then this is going to be 0. This lambda 4 times V4 is going to be 0. Then we have 3. Then we manage to reduce the 4 to 3 vectors. Now, getting that the 3 vectors themselves become what? It follows, therefore, from star that there exists lambda such that this is the case, and we have a linearly dependent case. Why? Because this lambda 1, lambda 2 were not all 0 in the first place. And so it will follow, therefore, that even here, when we have the lambda 1, the lambda 2, lambda 3 are not all what? Are not all 0. And therefore, see, if they're not all 0, it means we have a linearly dependent set. Right, with linearly dependent set. And this is let me see. Okay, there were 2 parts for this one.
Yeah, can we finish
Yes.
so I can rest? Because my exam is at 8 tomorrow.
I understand. Yeah, that's fine. Right. Okay, that's okay. So yeah, it's by and large what we have. So I think the next thing is I'll just send you some questions. Yeah, but you see, 8 is too early. Right.
Yeah,
I
it's
was
too
thinking
early.
it's too early to even claim that, because now it's like midnight already. It's like
Yeah.
it's 14 past 11. I would wish to send you some questions that it can be like tests, like to just, but short, not very long.
Okay, maybe you can send them. I'll try wake up early so I can
Yeah, that's the
try
thing. Like
them.
short,
Yeah.
just to test some
Okay, no
understanding. Like
problem.
standing, I'm looking at the trends, the kinds of things that you must know.
No, yeah.
Yeah, something like that. So I'm thinking of actually doing that. But yeah, I will most certainly, obviously, be in a position to send some questions. I'll just study again just the patterns in the many exams. Just identify key kinds of questions that if you really are
I
able
should
to
know.
do, yes, if you're able to do, then surely tomorrow you will actually, be in a position to get the most marks. Yeah, I will send those, but yeah, that'll be in the night. Okay.
Okay, yeah,
Yeah,
it's fine. I'll
yeah,
try wake up
in
early,
the
then I'll.
morning. Yeah, but there won't be too many. But also
Okay, yeah.
they're not long ones. They're just there to
Yeah.
just make sure that you just take note of like key things that you must know. Right. Well, thank you for
Yeah.
joining us today. Yeah, my goodness, I know very well. It's always a stretch. I feel that and this is what happens, that sometimes if you have a discussion like this, you feel that you should have, like, we should have had long discussions from the
More,
beginning.
yeah.
We should have had like long from the beginning, because then we'd have capitalized much on
Covered
time.
everything.
Yeah, we would have like covered everything. We would have had time to reflect and time to say, okay, what is difficult, what's not. But I know very well that, yeah. But what I can say, my few words, last words for this discussion is to say, this this word, these theoretical questions, the proofs that come at the end, they center around linear independence, and they center around the span, and
Basis.
basis and so on. Okay, so those are the kinds of concepts they center around. And so, yeah, so those are the kinds of things that you need to obviously take note of, because they will bring linear independent sets. So your proof now, what is very important in the proofs, you need to write. You don't think too much, but you write too much. That is the power
Yes.
of the proofs. Because in the proofs, there's no answer. It's not that the answer must be 2. It's whether there's some logic there. You're saying it's linear independent, then you can find scalars. Linearly independent, all the scalars are 0. Linearly dependent, you can find the scalars, but not all of them are 0.
That's it.
And you write those kinds of things, and you get marks from that. Anyone who's going to read the proofs are not perfect. No one
Yeah.
writes a perfect proof. But we look for sense and logical reasoning in there, and the fact that you're able to deduce from the fact that if it's linearly dependent, what does it mean? Then you can find scalars, not all 0, because linearly dependent, so that you can have that. Okay, we thank you so much for joining us.
Thank you.
Yeah, I'll send the recordings. I think, yeah, they were split into 2 or more recordings, because there was just
Okay.
that network interruption. Yeah, we thank you then, but I'm gonna send you some questions. I think I'm gonna wake you up early.
Yeah.
For 8.
Yeah.
Yeah, by around
Yeah.
6, by around 6, by around 5. Yeah, by around
Okay.
5, I think I'm gonna wake you up. Okay,
Okay, no problem.
yeah. Okay, we thank you, dear.
Thank you.
Yeah, okay, thank you, dear. All the best. Then we'll talk. I'll send the recordings, yeah, in the middle, yeah, in the night. So at some
Okay,
point.
thank you so much.
Okay, thanks, dear. All the best, and take care, and we chat on WhatsApp. And goodbye.
Bye.
Thanks, goodbye.